We're going to start off with Pascal Lee. We're about 15 minutes, well, not about, we are 15 minutes late. We're running 15 minutes late in the program. We'll try to keep that constant throughout the afternoon, rest of the afternoon. So Pascal is a head of the Mars Institute. He's also a PI at the SETI Institute. Should need no introduction. He was just running the Phobos Deimos conference, and he's an author of books, including children's books on Mission to Mars. And this year he's going to be the star of the upcoming movie Passage to Mars. Right, so please take it away, Pascal.
Thank you, Adrian. That's way too much information, though. Okay, so I'm going to give you a talk on maybe a subject that I consider a little bit speculative, and that is to see to what extent, well, first of all, whether and to what extent there might be a connection between Phobos and Deimos on the one hand and comets. Next. So the origin of Phobos and Deimos is still unknown, and as I mentioned just 5 minutes ago, there are three prevailing hypotheses. They are either captured small bodies from the outer main belt or beyond, and in that scenario, the canonical picture is that they are akin to D-type asteroids, because spectrally both Phobos and Deimos are D-type objects. And what that means is that you are very dark and very red. That's all being D-type means. So if you happen to be very dark and very red, you are a D-type person. But the truth is, D-type does not imply, well, it might imply that you contain volatiles, but not with evidence at hand. It might be implied simply by the fact that D-type asteroids are found mostly in the outer main belt and beyond, all the way into the Kuiper belt, and also among Jupiter's Trojans. So, in other words, they are from the outer part of the solar system, and therefore we suspect that they are rich in volatiles still from the beginning of the solar system, and also contain organics, which might account for the redness. But there's been, as of today, still no definitive, conclusive spectral detection of either water or organics on any D-type asteroid. That's really important to understand. So potentially, D-type could be a really big grab bag of things that might not be the same thing. For one thing, some lunar mare soils are so mature that they are actually quite dark and red, and they would actually exhibit a D-type spectrum. Okay, so, which of course would have nothing to do with the outer main belt objects being D-type. The second hypothesis is that Phobos and Deimos might be remnants of Mars's formation, and then the third hypothesis is that they might be reaccreted Mars impact ejecta. So today, this talk will be about speculating into the frontiers of what captured small bodies from the outer main belt and beyond might include. Next. So I want to first point out a couple of remarkable characteristics about Phobos and Deimos, in that they are characteristics that are remarkable because of their current heliocentric location. So next. First of all, in terms of their sizes, this is the top three largest near-Earth objects among the near-Earth object population. And so 1036 Ganymede is believed to be now the largest near-Earth asteroid. It's an S-type, as we'll see. 433 Eros has been explored by the Near-Shoemaker spacecraft. It's an S-type asteroid. And then the third one in line is 3552 Don Quixote. Okay, and we have never explored 3552 Don Quixote. Now, if you were to do this thought experiment to place Phobos and Deimos among the list of near-Earth asteroids in terms of their sizes, you would notice, next slide, that Phobos and Deimos would rank number 3 and number 5 respectively. Okay, so what this means is that as far as small bodies go, Phobos and Deimos are among the bigger objects that you would find in comparison to the near-Earth object population. Okay, among the largest. Now, there's only one near-Earth object that is intermediate in size between Phobos and Deimos, and that's 3552 Don Quixote. All right? Next slide. Now, spectrally, something interesting begins to emerge. Both Ganymede and Eros are S-type bodies, right? Whereas Don Quixote is a D-type asteroid. Right? Now, this is really remarkable because D-type asteroids among the near-Earth asteroid population are only 1.5% of the population among near-Earth asteroids. It's not like D-type asteroids are common. They're dark and red and somewhat harder to detect. They might actually represent a higher fraction than 1.5%. But of all the asteroids in the near-Earth asteroid population for which we have spectra that allows them to be assigned a type, only 1.5 turn out to be D types. Okay, so now we have this remarkable result or a realization that among the 5 largest small bodies in the inner solar system, okay, there are 3 D-type objects. Okay, next slide. So that's what I was. So I'm summarizing this here. Okay, so 35 Don Quixote, 52 Don Quixote is the only Nero that's intermediate in size. And it's really odd that it turns out to be a D-type asteroid as well. So what's up with Don Quixote? Next slide. Well, first of all, it was discovered in 1983 from Switzerland. And it was quickly realized that it was on a bizarre orbit. It's a Jupiter and Mars crosser. So it hasn't been in the inner solar system for a very long time. It's sort of been derived from the outer parts of the solar system. And the second thing to realize is that its orbital inclination is pretty high. It's 31 degrees, so it's not in the plane of the ecliptic. All right. So just from the orbital parameters alone, it was suggested that 3552 Don Quixote might be an extinct comet nucleus. Okay, so one of these comets that would have been captured in the inner parts of the solar system and one day would either crash into Jupiter or evolve towards the sun. Okay, next slide. And then just 2 years ago, in 2014, Momert et al. Revealed from IR observations at 4.5 microns using the Spitzer Space Telescope that Don Quixote is an active comet nucleus. Okay. So this is really exciting because now there's a connection, a one-to-one connection between D-type spectra and near-Earth objects and comets. So a faint coma and tail were detected, and emissions of molecular carbon dioxide as well. Water vapor was not detected, but it's suspected to be present as well. Okay, it's sort of a natural thing for comets to release. Next slide. So could Phobos and Deimos possibly be captured comet remnants? And by comet remnants, I mean it in all the possible ways. I mean, obviously, they might be just comet nuclei that have been captured somehow and have been petering out around Mars and are now what they are. Or they could have been broken up, reformed, included cometary material in, as a bulk component, as a major component in their reaccretion. So they could have had a complex evolution, but originally were they possibly derived from captured cometary materials? Okay. So that's the question. Next slide. So if you look at comets, ESA's Rosetta mission is exploring this 5-kilometer comet nucleus, whose name I will not attempt to pronounce. And you notice that the morphology of this particular nucleus is very different from either Phobos or Deimos. So for one thing, you couldn't claim on the grounds of just surface morphology and geology that somehow Phobos and Deimos even looked like a comet nucleus, at least not like this one. Next slide. But the truth is, we've actually now flown by several comet nuclei, and this is a nice montage that was done by the Planetary Society showing you the nuclei of Halley on the left, and then smaller comet nuclei that were flown by spacecraft over time. And Halley is of order the size of Phobos and Deimos, if you include the 2 lobes of Halley. Otherwise, these guys are all somewhat smaller. But you notice that the morphology of comet nuclei is not something that's really constant. They tend to show a surface with variegations, but some are relatively smooth and rounded with shallow craters, and others seem to have dramatic landscapes and even might be multiple components stuck together. Okay, so there really is no such thing so far as sort of your typical comet nucleus in terms of your look. And so therefore, you really could not exclude Phobos and Deimos on the grounds of somehow not looking enough like a comet. And again, this is just strictly from the morphology. We're not talking about composition yet. All right, next slide. Next. So how might they be cometary materials? Okay, so this is sort of a speculative scenario where Phobos and Deimos, because both are D-type objects, could be captured D-type bodies, but let's say they're not just volatile-rich asteroid. Let's say they are cometroids. They are actually, they were once comets and somehow were brought in. Okay, so in the scenario, the way they would fit in is that planetary migration took place. In other words, Jupiter, the giant planets moved out from the inner parts of the solar system out to where they are today during the migration phase of the formation of the solar system. That led to the disruption, the disturbance of lots of volatile-rich bodies in the outer solar system. They started to rain in. That was the heavy bombardment influx. And this heavy bombardment might have brought in volatile-rich D-type objects from the outer main belt and beyond. So this is sort of the canonical scenario for how Phobos and Deimos might have been captured D-type asteroids as well. Okay. Now, at that point, somehow the scenario requires you to have then this volatile-rich D-type material end up in a circular equatorial orbit around Mars. And I mentioned that even in the talk earlier, but that's a very difficult thing to do if you're sort of randomly captured by Mars, which is difficult to begin with, because you might usually just get slingshot and flung somewhere else into the solar system when you fly by Mars, as opposed to being captured. You have to slow down in order to sort of get captured. So maybe Mars had a thicker extended atmosphere early in its history. Maybe the body broke up. Maybe there was an impact with another moon in the Martian system that allowed some of these D-type materials to slow down and get into orbit around Mars. There are all kinds of scenarios that can be invoked to somehow capture an incoming asteroid or comet. But let's say you have captured fresh volatile-rich material in orbit around Mars, and it could be disrupted, and now in the form of a ring of debris, or it could still be a nucleus of an object. Well, over time, 2 minutes, over time, this nucleus will, that's newly arrived or newly reaccreted, is volatile-rich and D-type in Mars orbit, will erode from impact processing, get reduced in size, and build up a regolith, because a lot of the material that you eject from impacts on Phobos and Deimos actually comes back down onto Phobos and Deimos, as shown by Ramsey, for example, at this conference. So ultimately you end up with, in the case of Phobos, a body that might have experienced net erosion, so it was a larger moonlet in the past, and as it got eroded as well and is undergoing tidal stresses as it moves in towards Mars, is also fissuring. And the fissuring might be releasing volatiles, and we'll talk about that in a second. And then ultimately you keep building up, because you're recollecting all the ejecta over time, you're building up this caked layer that Eric Asbach has been describing of fine-grained powdery regolith that sort of continually recoats the surface. So you sort of keep hanging on to your ejecta, to your micrometeorite and meteorite impact ejecta. And so today's internal structure of Phobos might be something like this, where you have an inner core that's still rich in volatiles from the days it was captured as a cometroid, or from materials from the original ring of debris that reaccreted into a cometroid, and then surrounded by a very processed and eroded and fissured layer, and that's sort of crusted by this caked material. For Deimos, the morphology is quite different. The density of Deimos is also really low, and so Deimos might actually be a rubble pile with a thick regolith around it, which would account for sort of a much smoother topography. So, in other words, we might be dealing in this sort of a thought experiment with two objects that actually have a direct connection with cometary objects, a la Don Quixote, going all the way back to the formation of planets and the heavy bombardment phase of the formation of the solar system. Next slide. Okay, so I just want to point out that this idea that Phobos could be volatile rich and releasing and venting gases is not even new. Even Bill Hartman, as recently as 2007, contributed a paper where he suggested that the grooves on Phobos might be places where volatile rich interior was venting into the Martian system. Next slide. So I'll just wrap up by saying that I don't personally believe that this is a likely explanation and scenario. The capture theory hypothesis has major problems, but it's definitely still part of the trade space. And it's one that's particularly intriguing because if you can imagine that Phobos and Deimos could actually be cometary material, they could have a very high water fraction still in their interior. Yuta Tagake actually showed during this recent Phobos Deimos conference that if you assume that the rock fraction of Phobos and Deimos is a sort of similar to CM chondrites in composition, Phobos and Deimos could have respectively up to 37 to 55% by mass in their water fraction. Okay. Now there are many caveats, of course.